The colorimetric titration curve is obviously smooth, and this is because the iodine necessary for the Karl Fischer reaction is generated by the electrochemical reaction, which is not only continuous but is also controlled minutely. The endpoint is determined as the point where the polarizing potential, or the electrolyzing velocity, returns to the same place as the starting point, or it reaches the upper threshold of the endpoint. The weight of water is calculated as the integration value of the elapsed time and the electrolyzing velocity, which is indicated at the top display of the colorimetric titration analyzer, and about which I will speak soon. The concentration of water is, again, calculated as the water weight divided by the sample weight. The amount of iodine generated by the electrochemical reaction is proportional to the quantity of the electricity and is calculated following Faraday's law. The quantity of the electricity is calculated as the integration value of the elapsed time and the electrical current. 1 mole of iodine, for example, is generated with 192,970 coulombs of electricity, which is double Faraday's constant, 96,485 coulombs per mole. Because 1 mole of iodine corresponds to 1 mole of water in the Karl Fischer reaction, 192,970 coulombs of electricity corresponds to 18.02 grams of water. When this relation is converted into the value per water weight, 10.71 coulombs of electricity corresponds to 1 milligram of water. In more minute units, 1 microgram of water is equivalent to 10.71 millicoulombs of electricity, the electrical current of 10.71 milliamperes in 1 second. The electrolyzing velocity is calculated from the electrical current in the same way as mentioned before and displayed digitally as micrograms per second at the top of the analyzer. I hope you can now understand fully the reason why colorimetric titration is suitable for measuring trace amounts of water. Before moving to another topic, I would like to wrap up our explanation so far by comparing the two titration methods. This table has 5 points of comparison: principal, reagents, features, preferable water content range, and preferable kinds of samples. First, regarding the reagents, 2 kinds of reagents are in general used for both titration methods. In volumetric titration, the titrant and the dehydrating solvent illustrated in italics are necessary. We provide various kinds of dehydrating solvents, such as general use, for oils, for sugars, for ketones, and others. And thus, volumetric titration is applicable for various natures of samples. This is the main feature of volumetric titration. For colorimetric titration, we also need 2 reagents. One is the anode solution, and the other is the cathode solution. However, there are only 2 kinds of anode solutions illustrated in italics. One is general use, and the other is for ketones. Thus, colorimetric titration is applicable for limited kinds of samples. Colorimetric titration is not applicable for samples that foul the electrodes or interfere with the normal iodine generation that helps achieve accurate measurements. On the other hand, colorimetric titration is suitable for trace amounts of water. It can be applied for low moisture samples, the water concentration of which is in the range of several parts per million and several percentage points. Volumetric titration is better than colorimetric titration for high moisture samples in the concentration range of several hundred parts per million and several tens of percentage points. You can choose between your preferable titration methods by referring to this comparison table, depending on the nature of your samples. I also recommend that you have both titration type analyzers if you have to handle samples of various natures or with a wide range of water concentrations. Next, I will explain the operation procedures. The ordinary procedures of both kinds of titration are illustrated in this slide, and I would like to point out the importance of these orange-colored calibrations with distilled water before and after the sample measurements to confirm the reliability of such measurements. In the case of volumetric titration, I recommend strongly that you check the conditions of the analyzer and the reagents before the actual sample measurements by analyzing once or twice 10 microliters of distilled water and confirming that the recovery ratios and the measuring time are nearly 100% and less than 3 minutes, respectively. After making actual sample measurements, for instance, after a 1-hour operation with 9 measurements of 3 samples and 3 cycle measurements each, you had better analyze another 10 microliters of distilled water. When both the recovery ratio and the measuring time are almost the same as the ones before the actual sample measurements, the measurement results are reliable. Similar calibrations with distilled water before and after actual sample measurements by using 5 instead of 10 microliters of distilled water are strongly recommended also in the colorimetric titration. I will now describe the routine and practical maintenance of the analyzer and also about abnormal diagnosis. First of all, I would like to recommend again that you confirm that the analyzer works well by measuring distilled water or the standard sample before and after the actual sample measurements. Secondly, the proper measuring time is, in general, approximately 5 minutes. You should suspect some interference with the Karl Fischer reaction if the measuring time exceeds 10 minutes. One of 2 typical exceptions to this recommendation is in cases where the solid samples are difficult to dissolve, and the other is when you use the optional water vaporizer. Thirdly, regarding accuracy, since all analyses fundamentally have some errors, the accuracy of the analysis is determined by its repeatability. The standard criteria of 2 Karl Fischer titrations are shown in the table, which lists the recommended RSDs, relative standard deviations, of volumetric and colorimetric titrations in 3 ranges of sample water content, since the accuracy is apt to decline in accordance with the decrease of the measured water. I can determine the relative standard deviation with calculations as follows. When the results of 3 cycle measurements of one sample are 80, 100, and 120 parts per million, the average of these values is 100 parts per million, and the standard deviation is 20 parts per million. The RSD, relative standard deviation, becomes 20%, which is between 10 through 30% within the standard criteria. You can trust that this measurement is done properly. On the other hand, if the 3 measured values are 50, 100, and 150 parts per million, the relative standard deviation is 50%, and you should doubt the reliability of this measurement. Now I will explain what to do when abnormal incidents occur, such as overly long or overly short measuring times or low accuracy. The first thing that I recommend is to clean the detection electrode, the most important part of the analyzer. Please extract it from the chamber and wipe its surface gently with a clean tissue or something similar. If this cleaning does not produce the desired results, please try new reagents. If the new reagents also do not work well, please do not hesitate to contact us. We will let you know the most appropriate countermeasures corresponding to the nature and conditions of the sample. One example of such countermeasures is the use of the optional water vaporizer, which vaporizes the water of the samples that contain chemical compounds which interfere with the Karl Fischer reaction. I would like to explain in the next 2 slides about interference in the Karl Fischer reaction and countermeasures to deal with such interference. To tell the truth, there are various interfering substances in the Karl Fischer reaction. Since details about them are described in pages 39 to 45 of the technical manual, I recommend that you read them. In this presentation, I will summarize them. As I mentioned in an earlier slide, the Karl Fischer reaction is an oxidation-reduction reaction which proceeds when the 5 key compounds, iodine, sulfur dioxide, base, water, and methanol, exist in the same reaction medium. Thus, such substances as can react with these 5 key compounds individually could interfere with the Karl Fischer reaction, and we have some countermeasures against them. The first category of interfering substances includes ketones, aldehydes, and amines, and amino alcohols with a pKa above 9. These substances react with methanol to form water or react with iodine, and as a result, they make the observed values higher than the actual ones. The countermeasure against ketones, aldehydes, and carboxylic acids is to use the dehydrating solvent for ketones or the anode solution for ketones. In the case of amines, adding a weak acid such as salicylic acid into the reaction medium is an effective way to prevent interference. Interfering substances in the second category react with iodine to form iodide anions, or react with hydrogen iodide to form water, and as a result they make the observed values higher. The third category, in contrast, includes substances that react with iodide anions to form iodine and decrease the observed values. I regret to say this type of interference cannot be prevented by selecting suitable reagents. The only countermeasure is to apply the optional water vaporizer unless the samples are thermally unstable. Other types of interfering substances are listed in the technical manual. Since the Karl Fischer titration is based on a chemical reaction, some substances exist for which the water could never be measured with this titration.